Lasers will release pulses of light waves. And in this problem, the question is how many photons are produced in a laser pulse of 0.466 joules at 549 nanometers. So what we have to realize here is a couple of things. What are we given? We are given the wavelength, right? That's the wavelength, but that's the wavelength of each wave. This laser does not release just one wave. It releases many, many, many waves. So this individual wave has an energy, this individual wave has an energy, this individual wave has an energy, and combined, the total energy of all of these waves is given to us as 0.466 joules. That's this right over here. So we have to find the energy of a single wave, and then that will allow us to determine how many waves are in this total energy. So here we go. What is the energy of this wave, that wave, that wave, and then we add them all up to there. So the energy of a single photon, and again I use the word photon and wave interchangeably, is going to be, we have a wavelength, and we have, so based off of the wavelength, we can find the energy of a single photon. And that's going to be this formula right here, the HC over lambda. Let's go ahead and get that answer. 6.626 times 10 to the minus 34th joules seconds. That's Planck's constant. Speed of light, 2.998 times 10 to the 8th meters per second. Very fast. And the wavelength is in nanometers, but once again, we need to have it in meters. And the conversion from nanometers to meters, nanometers is 10 to the minus 9th. And so there we go. And this will give us the energy of just one wave. Now, we do this calculation. Let's go ahead and plug this in. 6.626, 10 to the minus 34th, 2.998. 10 to the 8th divided by 549, 10 to the minus 9th, and we get the energy of a single photon is 3.618 times 10 to the minus 19th joules. Now I'm circling this, but this is not my final answer. This is for one single photon. The pulse, the laser pulse, pulses out 0.466 joules. And so we're going to do this then. 0.466 joules is the total energy, but one single photon provides this energy, 3.618, 10 to the minus 19th joules. And now that would give me the number of photons. I'm going to go ahead and this here, invert it, and then times 0.466. So I get I got three significant digits. So it's 1.29 times 10 to the 18th photons. And so that is my answer. Again, these formulas are for single waves, but in this problem we had to figure out the energy of a single wave and then use that to determine how many waves there are in a total energy given.